Hello, this is Physics 1020 and 1090. This is a lecture for Wednesday, March 18th. We're still in chapter 24 on wave optics. This is the third video in the lecture, and we're going to continue talking about polarization. Just review a little bit from the last video you saw. Polarization has two states. You have electromagnetic wave, which has electric field that goes up and down, and it propagates in this direction here. But there's two possibilities for the electric field. It can be going up, down, or this line, which is supposed to be drawn sort of into and out of the paper. This is going to be going left, right, left, right. So if the electric field is moving in this direction here, it has two polarization states corresponding to two directions of electric field. You pass that through a polarizer, and that little line in the polarizer indicates which electric field passes through. It'll pass the electric field going left, right, left, right. It will not. It will absorb the electric field going up, down, up, down. So afterwards, you now have linearly polarized light, which only the electric field going left, right, and half of the intensity. Let's kind of look at the situation we saw last video, but we're going to give it a little bit of a twist. Okay, we'll begin with unpolarized light here. The electric fields are going back, up and down, back and forth, left and right, all in sort of a random way with intensity I0. We pass that light through a polarizer. And now with the polarizer is going to pass the light going left, right. It's going to absorb the light going up, down, and you have half the intensity. That's exactly what we saw last video. Let's make it a little more complicated. Just like last video, we're going to put in a second polarizer over here. And this is going to be crossed polarizer. That is, the pass line is going to be perpendicular between this one and this one. So you now have linearly polarized light going left, right. And if it went through this cross polarizer, and that was all there was, all of that light would be absorbed. None of the light would pass through. No light would get through. We saw that last video. This is a case of cross polarizers. No light gets through. But of course, we're going to make it a little more complicated still. We're going to put in a third polarizer. Aha. So now we have our unpolarized light. It goes through a polarizer. The electric field's going left, right, half the intensity. And now it's going to go through a polarizer that's aligned 45 degrees to this original polarizer. So the question now is, what happens here and what happens out here? So first, let's look at the light in this area and see if we can analyze that, similar to what we did last class. Okay, so now we're looking at the light coming straight out of the paper now, right at us. You have, before the polarizer, the second polarizer, you had linearly polarized light. It was going left, right. That's this vector E. We resolved that vector into two components along the 45-degree line because that polarizer was aligned at 45 degrees. So now you have two components, a parallel component and a perpendicular component. This angle is 45 degrees, that's 90 degrees, it's a little triangle. You can write that the parallel component is E, the hypotenuse, the original electric field, times cosine of theta, in this case cosine of 45. Cosine of 45 is square root of 2, 1 over square root of 2. So the electric field strength is E over square root of 2. So after it goes through that second polarizer, it's now has an electric field that's aligned along the 45-degree direction. And because square root of cosine of 45 is 1 over square root of 2, it has half of the light that came before. So before the second polarizer, you have an intensity, and afterwards you have half that intensity. That's just the law of Malus. The thing I want to stress is that this light comes out oriented in the 45-degree direction. So we had originally unpolarized light go through this, is now polarized, left, right, goes through this 45-degree polarizer, And again, half the intensity is gone, and now the electric field's at the 45-degree angle. So here your intensity I0. Here you lose half because you always lose half when unpolarized light goes through a polarizer. Here you lose another half because of the law of Malus and at 45 degrees. Now what happens through the last polarizer? This is the key question. Well, we'll look at it as before. Now we have, before the last polarizer, the electric field going at the 45-degree angle. You can resolve that into two electric fields, one going parallel to the axis, one perpendicular. That's the axis of that third polarizer, which was straight up and down. Again, this is a little triangle. You can find the parallel component is E cosine of the angle, which is 45. So after the third polarizer, the light's now going completely up and down, and it's half the intensity. Cosine of 45 is 1 over square root of 2. The square to get the intensity gives you a half. So this really should be I before is equal, I after is I before over 2. So here's the whole story. You started with unpolarized light. You went through a polarizer, going left, right, half the intensity. You go to a 45-degree polarizer, and now the light's polarized at an angle of 45, and it's a fourth of the intensity. And now you go through a polarizer that's up and down, and it comes out, and now you have polarization up, down. It's 1/8 the intensity. Now, why is this so amazing? Well, what's amazing is if you didn't have this polarizer in there, if you took that out, you have two cross polarizers, and you expect no light whatsoever. So by inserting this third polarizer, all of a sudden, light gets through. So it's almost like magic. You designed a way to block out all the light with two cross polarizers, and then the third polarizer rotates the light so it gets through, and now you have some light getting through the two cross polarizers. So I want to show you an example. And to show you the example, I'm going to turn my computer around to the light source, and we're going to look at what happens in this case. Okay, I have my polarizing sheets. So I have one polarizing sheet here, another polarizing sheet, and I'm going to take those two and I'm going to cross them so that no light gets through. So let's see, we want to get there, right there. No light gets through. Two cross polarizers. Now I'm going to take another sheet and I'm going to slip it in here. And all of a sudden, some light gets through. So, two cross polarizers. No light gets through. But the insertion of another polarizer at some funny angle and light gets through. It won't if it's at the same angle as either of the two. But if we come in around a 45-degree angle, all of a sudden, light gets through. That is the magic of polarization. What that means is you can look through at two cross polarizers. If you want to study and decide, is this polarizing sheet indeed a polarizing sheet? Is it some material that polarizes or not? You can look through two cross polarizers and then look at the sheet you're interested in, and if it causes light to go through, this sheet is a polarizer too. All right, now let me just note that this is how a polarized light microscope works. You can take unpolarized light, send it through a polarizer, then send it through an analyzer. They're crossed. No light should get through. Then you can put your sample in between them. If your sample has polarization effects, if it's a type of material that polarizes light, you can rotate that sample around and you should be able to see light getting through your analyzer. However, if it's just an unpolarizing material, which is most materials, it just doesn't cause light polarization, no light gets through and everything's always dark. So people for instance, who study rocks will often want to understand the polarization effects of different rocks. They'll make thin samples of the rock. They'll pass it through a polarized light microscope and study how the polarization changes as they rotate the rocks. Dr. Jha here in the Department of Physics at Oakland University studies cartilage, and one of the methods he uses is a polarized light microscope. Cartilage is a material that has fibers, a lot of collagen fibers that are lined with each other. Any tissue or any material that's made up of a lot of fibers aligned has a potential to be polarizing. So collagen actually is a polarizing material. So he takes a polarized light microscope, cross polarizers, you should see nothing, but if you slip a sample of the collagen from the surface of the bone, of the cartilage of the bone in between, you can find interesting properties of that material. If you're interested in this kind of behavior, I'm going to send you again some physics girl video where you can look at materials and see their polarization effects through cross polarizers. For instance, if you just use tape has a lot of stretched fibers inside the material. If you just would attach tape as that third polarizer, you'll be able to see all kinds of interesting effects through the polarized light microscope. Okay, next lecture, we're going to talk about a little more about polarization. You can get polarization from scattering, from reflection, and then we'll be done with chapter 24.